Class 11, Unit 4 Chemical Bonding and Molecular Structure. Scientists are constantly discovering new compounds, orderly arranging the facts about them, trying to explain with the existing knowledge, organizing to modify the earlier views, or evolve theories for explaining the newly observed facts. Matter is made up of one or different types of elements. Under normal conditions, no other element exists as an independent atom in nature except noble gases. However, a group of atoms is found to exist together as one species having a characteristic properties. Such a group of atoms is called a molecule. Obviously, there must be some force which holds these constituent atoms together in the molecules. The attractive force which holds together various constituents together in different chemical species is called a chemical bond. Since the formation of chemical compounds takes place as a result of combination of atoms of various elements in different ways, it raises many questions. Why do atoms combine? Why are only certain combinations possible? Why do some atoms combine while certain others do not? Why do molecules possess definite shapes? To answer such questions, different theories and concepts have been put forward from time to time. These are Gaussian-Lewis approach, valence shell electron pair repulsion theory, valence bond theory, and molecular orbital theory. The evaluation of various theories of valence and the interpretation of the nature of chemical bonds have closely been related to the developments in the understanding of the structure of atom, the electronic configuration of elements, and the periodic table. Every system tends to be more stable, and bonding is nature's way of lowering the energy of the system to attain stability. 4.1 Gaussian-Lewis approach to chemical bonding. In order to explain the formation of chemical bond in terms of electrons, a number of attempts were made, but it was only in 1916 when Gaussian and Lewis succeeded independently in giving a satisfactory explanation. They were the first to provide some logical explanation of valence, which was based on the inertness of noble gases. Lewis pictured the atom in terms of a positively charged kernel, the nucleus plus inner electrons, and the outer shell that could accommodate a maximum of 8 electrons. He further assumed that these 8 electrons occupy the corners of a cube which surrounded the kernel. Thus, the single outer shell electron of sodium would occupy one corner of the cube, while in the case of a noble gas, all the 8 electrons would be occupied. This octet of electrons represents a particularly stable electronic arrangement. Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. In the case of sodium and chlorine, this can happen by the transfer of an electron from sodium to chlorine, thereby giving the Na plus and Cl minus ions. In the case of other molecules like Cl2, H2, F2, etc., the bond is formed by sharing of a pair of electrons between the atoms. In the process, each atom attains a stable outer octet of electrons. Lewis symbols. In the formation of a molecule, only the outer shell electrons take part in a chemical combination, and they are known as valence electrons. The inner shell electrons are well protected and are generally not involved in the combination process. G. N. Lewis is an American chemist introduced simple notations to represent valence electrons in an atom. These notations are called Lewis symbols. For example, the Lewis symbols for the elements of second period are as under. Significance of Lewis symbols. The number of dots around the symbols represents the number of valence electrons. This number of valence electrons helps to calculate the common or group valence of the element. The group valence of the elements is generally either equal to the number of dots in Lewis symbols or 8 minus the number of dots or valence electrons. Kossel, in relation to chemical bonding, drew attention to the following facts. In the periodic table, the highly electronegative halogens and the highly electropositive alkali metals are separated by the noble gases. The formation of a negative ion from a halogen atom and a positive ion from an alkali metal atom is associated with the gain and loss of an electron by the respective atoms. The negative and positive ions thus formed attain stable noble gas electronic configurations. The noble gases, with the exception of helium which has a duplet of electrons, have a particularly stable outer shell configuration of 8 electrons octet Ns2Np6. The negative and positive ions are stabilized by electrostatic attraction. For example, the formation of NaCl from sodium and chlorine, according to the above scheme, can be explained as Na plus an electron. Cl plus electron is Cl minus. Therefore, Na plus Cl minus gives NaCl or Na plus Cl minus. Similarly, the formation of CaF2 may be shown as Ca is equal to Ca2 plus 2 electrons. Fa plus electron gives F minus. Therefore, Ca2 plus 2 F minus gives CaF2 or Ca2 plus F minus 2. The bond formed as a result of electrostatic attraction between the positive and negative ions was the electrovalent bond. The electrovalence is thus equal to the number of unit charge on the ion. Thus, calcium is assigned a positive electrovalence of 2, while chlorine a negative electrovalence of 1. Causel's postulations provide the basis for the modern concepts regarding ion formation by electron transfer and the formation of ionic crystalline compounds. His views have proved to be of great value in the understanding and systemization of the ionic compounds. At the same time, he did recognize the fact that a large number of compounds did not fit into these concepts. 4.1.1 Octet rule. Kossel and Lewis in 1916 developed an important theory of chemical combination between atoms known as electronic theory of chemical bonding. According to this, atoms can combine either by transfer of valence electrons from one atom to another, by gaining or losing, or by sharing of valence electrons in order to have an octet in their valence shells. This is known as octet rule. 4.1.2 Covalent bond. Langmuir, 1919, refined the Lewis postulations by abandoning the idea of the stationary cubical arrangement of the octet and by introducing the term covalent bond. The Lewis-Langmuir theory can be understood by considering the formation of the chlorine molecule Cl2. The Cl atom with electronic configuration Ne3s23p5 is one electron short of the organ configuration. The formation of the Cl2 molecule can be understood in the terms of the sharing of a pair of electrons between the two chlorine atoms, each chlorine atom contributing one electron to the shared pair. In the process, both chlorine atoms attain the outer shell octet of the nearest noble gas, that is argon. The dots represent electrons. Such structures are referred to as Lewis dot structures. The Lewis dot structure can be written for other molecules also, in which the combining atoms may be identical or different, the important conditions being that each bond is formed as a result of sharing of an electron pair between the atoms. Each combining atom contributes at least one electron to the shared pair. The combining atoms attain the outer shell noble gas configuration as a result of the sharing of electrons. Thus, in water and carbon tetrachloride molecules, formation of covalent bonds can be represented as below. Thus, when two atoms share one electron pair, they are said to be joined by a single covalent bond. In many compounds, we have multiple bonds between atoms. The formation of multiple bonds envisages sharing of more than one electron pair between two atoms. If two atoms share two electron pair of electrons, the covalent bond between them is called a double bond. For example, in the carbon dioxide molecule, we have two double bonds between the carbon and oxygen atoms. Similarly, in ethene molecule, the two carbon atoms are joined by a double bond. When combining atoms share three electron pairs, as in the case of two nitrogen atoms in the N2 molecule, the two carbon atoms in the ethine molecule, a triple bond is formed. 4.1.3 Lewis representation of simple molecules, the Lewis structures. The Lewis dot structures provide a picture of bonding in molecules and ions in terms of the shared pair of electrons and the octet rule. While such a picture may not explain the bonding and behavior of a molecule completely, it does help in understanding the formation and properties of a molecule to a large extent. Writing of Lewis dot structures of molecules is therefore very useful. The Lewis dot structures can be written by adopting the following steps. The total number of electrons required for writing the structures are obtained by adding the valence electrons of the combining atoms. For example, in the CH4 molecule, there are 8 valence electrons available for bonding, 4 from carbon and 4 from the 4 hydrogen atoms. For anions, each negative charge would mean addition of one electron. For cations, each positive charge would result in the subtraction of one electron from the total number of valence electrons. For example, for the CO3 2 minus ion, the two negative charges indicate that there are two additional electrons than those provided by the neutral atoms. For NH4 plus ion, one positive charge indicates the loss of one electron from the group of neutral atoms. Knowing the chemical symbols of the combining atoms and having knowledge of the skeletal structure of the compound known or guessed intelligently, it is easy to distribute the total number of electrons as bonding shared pairs between the atoms in proportion to the total bonds. In general, the least electronegative atom occupies the central position in the molecule or ion. For example, in the NF3 and CO2 minus 3, nitrogen and carbon are the central atoms where fluorine and oxygen occupy the terminal positions. After accounting for the shared pairs of electrons for single bonds, the remaining electron pairs are either utilized by for multiple bonding or remain as the lone pairs. The basic requirement being that each bonded atom gets an octet of electrons. Lewis representation of a few molecules or ions are given in the table 4.1, page number 104, 4.14, formal charge. Lewis dot structures in general do not represent the actual shapes of the molecules. In case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. The formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. It is expressed as formal charge of an atom in a Lewis structure is equal to total number of valence electrons in the free atom minus total number of non-bonding, that is lone pair electrons, minus half of total number of bonding or shared electrons. The counting is based on the assumption that the atom in the molecule owns one electron of each shared pair and both the electrons of a lone pair. Let us consider the ozone molecule O3. The Lewis structure of O3 may be drawn as below. The atoms have been numbered as 1, 2, and 3. The formal charge on the central atom O marked 1 is equal to 6 minus 2 minus half into 6, which is equal to plus 1. The end oxygen atom marked 2 is equal to 6 minus 4 minus half into 4 is equal to 0. The end atom marked 3, 6 minus 6 into minus half into 2 is equal to minus 1. Hence, we represent O3 along the formal charges as follows. We must understand that formal charges do not indicate real charge separation within the molecule. Indicating the charges on the atoms in the Lewis structure only helps in the keeping track of valence electrons in the molecules. Formal charges help in the selection of the lowest energy structure from a given number of possible Lewis structures for a given species. Generally, the lowest energy structure is the one with the smallest formal charges on the same. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. 4.1.5 Limitations of the octet rule. The octet rule, though useful, is not universal. It is quite useful for understanding the structures of most of the organic compounds and it applies mainly to the second period elements of the periodic table. There are three types of exceptions to the octet rule. The incomplete octet of the central atom. In some compounds, the number of electrons surrounding the central atom is less than 8. This is especially the case with elements having less than 4 valence electrons. Examples are LiCl, BeH2, and BCl3. Li, Be, and B have 1, 2, and 3 valence electrons only. Some other such compounds are AlCl3 and BF3. Odd electron molecules. In molecules with an odd number of electrons like nitric oxide NO and nitrogen dioxide NO2, the octet rule is not satisfied for all the atoms. The expanded octet. Elements in and beyond the third period of the periodic table have, apart from 3s and 3p orbitals, 3d orbitals also available for bonding. In a number of compounds of these elements, there are more than 8 valence electrons around the central atom. This is termed as the expanded octet. Obviously, the octet rule does not apply in such cases. Some of the examples of such compounds are PF5, SF6, H2SO4, and a number of coordination compounds. Interestingly, sulfur also forms many compounds in which the octet rule is obeyed. In sulfur dichloride, the S atom has an octet of electrons around it. Other drawbacks of the octet theory. It is clear that the octet rule is based upon the chemical inertness of noble gases. However, some noble gases, for example xenon and krypton, also combine with oxygen and fluorine to form a number of compounds like XeF2, KrF2, XeOF2, etc. This theory does not account for the shape of molecules. It does not explain the relative stability of the molecules being totally silent about the energy of a molecule. 4.2 Ionic or electrovalent bond. From the Kossel and Lewis treatment of the formation of an ionic bond, it follows that the formation of ionic compounds would primarily depend upon the ease of formation of the positive and negative ions from the respective neutral atoms, the arrangement of the positive and negative ions in the solid, that is, the lattice of the crystalline compound. The formation of a positive ion involves ionization, that is, removal of electrons from the neutral atom, and that of the negative ion involves the addition of electrons to the neutral atom. The electron gain enthalpy, delta EGH, is the enthalpy change when a gas phase atom in its ground state gains an electron. The electron gain process may be exothermic or endothermic. The ionization, on the other hand, is always endothermic. Electron affinity is the negative of the energy change accompanying electron gain. Obviously, ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. Most ionic compounds have cations derived from metallic elements and anions from non-metallic elements. The ammonium ion NH4 made up of two non-metallic elements is an exception. It forms the cations of a number of ionic compounds. Ionic compounds in the crystalline state consist of orderly three-dimensional arrangements of cations and anions held together by Coulombic interactions energies. These compounds crystallize in different crystal structures determined by the size of the ions, their packing arrangements, and other factors. The crystal structure of sodium chloride NaCl or rock salt, for example, is shown below. In ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive, but still the crystal structure gets stabilized due to the energy released in the formation of the crystal lattice. For example, the ionization enthalpy for Na plus formation from Na is 495.8 kJ per mole, while the electron gain enthalpy for the change Cl plus electron gives Cl minus is minus 348.7 kilojoules per mole only. The sum of the two, 147.1 kilojoule per mole, is more than compensated for by the enthalpy of lattice formation of NaCl, that is minus 788 kg per mole. Therefore, the energy released in the processes is more than the energy absorbed. Thus, a qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species in gaseous state. Since lattice enthalpy plays a key role in the formation of ionic compounds, it is important that we learn more about it. 4.2.1 Lattice enthalpy. The lattice enthalpy or energy of an ionic solid is defined as the energy required to completely separate one mole of a solid ionic compound into gaseous constituent ions. For example, the lattice enthalpy of NaCl is 788 kilojoules per mole. This means that 788 kilojoules of energy is required to separate one mole of solid NaCl into one mole of Na plus gaseous atoms and ions and one mole of Cl minus gaseous ions to an infinite distance. This process involves both the attractive forces between ions of opposite charges and the repulsive forces between ions of like charge. The solid crystal being three-dimensional, it is not possible to calculate lattice enthalpy directly from the interaction of forces of attraction and repulsion only. Factors associated with the crystal geometry have to be included. 4.3 Bond parameters. 4.3.1 Bond length. Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Bond lengths are measured by spectroscopic, X-ray diffraction and electron diffraction techniques about which you will learn in higher classes. Each atom of the bonded pair contributes to the bond length as shown in figure 4.1. In the case of a covalent bond, the contribution from each atom is called the covalent radius of the atom. The covalent radius is measured approximately as the radius of an atom's core, which is in contact with the core of an adjacent atom. in a bonded situation. The covalent radius is half of the distance between two similarly atoms joined by covalent bond in the same molecule. The van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded situation. Further, the van der Waals radius is half of the distance between two similar atoms in separate molecules in a solid. Covalent and van der Waals radii of chlorine are depicted in Figure 4.2. Some typical average bond lengths for single, double, and triple bonds are shown in Table 4.2. Bond lengths for some common molecules are given in Table 4.3. The covalent radii of some common elements are listed in Table 4.4. 4.3.2 Bond angle. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. Bond angle is expressed in degree, which can be experimentally determined by spectroscopic methods. It gives some idea regarding the distribution of orbitals around the central atom in a molecule or complex ion, and hence it helps us in determining its shape. For example, HOH bond angle in water can be represented as under 4.3.3 Bond enthalpy. It is defined as the amount of energy required to break one mole of bonds of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoules per mole. For example, the HH bond in hydrogen molecule is 435.8 kilojoules per mole. Similarly, the bond enthalpy for molecules containing multiple bonds, for example O2 and N2, will be as under 498 kJ per mole for oxygen and 946.0 kilojoules per mole for nitrogen. It is important that larger the bond dissociation enthalpy, stronger will be the bond in the molecule. For a heteronuclear diatomic molecule like HCl, we have 431.0 kilojoules per mole. In case of polyatomic molecules, the measurement of bond strength is more complicated. For example, in case of H2O molecule, the enthalpy needed to break the two OH bonds is not the same. For H2O molecule, 502 kilojoules per mole and OH 427 kilojoules per mole. The difference in the delta AH negative values shows that the second OH bond undergoes some change because of changed chemical environment. This is the reason for some difference in energy of the same OH bond in different molecules like C2H5OH, ethanol, and water. Therefore, in polyatomic molecules, the term mean or average bond enthalpy is used. It is obtained by dividing total bond dissociation enthalpy by the number of bonds broken, as explained below in the case of water molecule. Average bond enthalpy is equal to 502 plus 427 by 2, which is equal to 464.5 kilojoules per mole. Thank you. The next part, 4.3.4 bond order, will be done in the part 2 of the coming series.